Hello and good morning, and look what we're doing today.
Slopes of inverse functions. We've been talking about inverse functions, but of course to put this, we really need to talk about derivatives. And we know derivatives come from these tangent lines, the slopes of the best linear approximation to a function, right?
Yeah, and in fact, if we take the best linear approximation and think of it like a little tangent toothpick, we can chain these toothpicks up and just create the function that way.
We could, which would be doing differential equations. Let's start with a really simple example, a single toothpick.
Yeah, a single toothpick.
So we'll start with a single line. And the nice thing about, well, let's bring up this chart. Oh, so here's a nice little line. Okay?
Yeah.
I took a kind of funny one. I took one that goes through the point 1, 2. So here it goes right through this point there. And here's my equation. Y is equal to 2 plus 6 times x minus 1. The nice thing about this equation, it's a linear equation, so when I reflect it across a line, it's still going to be a line. So that means I can write down the equation for that line. It's not too hard to see what it'll be, because you just have to move the x by itself and move everything else onto y. So that's a little bit of algebra.
Yeah, and that's the basic switching x and y positions.
Switching x and y's. So I'm going to do this on my cool little Desmo application. Let's see what happens when I rotate this. So my straight line that had a slope of 6 rotates down. It's got a much lower slope. You can see now it goes through the point 2, 1, okay, because my x's and y's have switched places. And now my equation, x in terms of y, is 1 plus 1/6 y minus 2. So what I really want you to notice, Matt, is this 6 becomes a 1 over 6.
The slopes are the reciprocals.
They're the reciprocals of each other. And that's just because of the rotation or the reflection across
The reflection, and we discussed how simple geometry can show us how to do that reflection.
That's right.
So the reflection part is intrinsic to our friend
the inverse
function, and that's why we did some geometry discussion earlier about exactly how this reflection works.
Exactly. Now I took this funny function, I mean, y2 and a 6, what am I thinking? Well, it's because it came from our earlier example. We had a cubic function. Here's our cubic function. And I picked the point 2, 1. Okay, maybe I'll remember the cubic function here. 2 times x to the cube, and the inverse is basically y over 2 to the 1/3. We take this same point, 1, 2.
And it's going to go to 2, 1.
Go to 2, 1. And my straight line, y is equal to 2 plus 6 x minus 1. The one we just saw in that last example. When we rotate it, it's going to go to, can you remember, Matt?
Yeah, it's going to be a constant with 1/6 as the slope,
Exactly.
and it's shifted.
There's that 1/6. Hello, 1/6.
Yeah, perfect. So the slopes are going to reciprocals.
They're going to reciprocals. Now, we're going to do, we had this nice example with a sine where we just sketch everything by hand. Let's take a look at that.
Yes.
Because this is going to show us a bit more about the details. So here's my sine function. Okay, y is equal to sine of x. I got it mapped out right there, sine of x. When I invert the function, oh, I did something a little bit wrong there, but that's okay. We'll fix that. It should be sine inverse of y. We can fix that. Do I want to fix it? Nah. Well, maybe I do.
Yeah, x can't be in both sides, so yeah, sine inverse of y.
Yeah. Are we happy now?
There we go.
I'm so happy. Okay, now let's remember we can't use the whole.
Yeah, I'm just going to ask you about that, because what happens when we go past the maximum?
What'll happen is the sine function will sort of, when we rotate it up, it'll sort of flip on top of itself. So let's just stop at the maximum. I can do that like this.
Okay, stopping it at the maximum.
And here I can show a tangent line to the curve. And here's a little equation for the straight line.
And what is that? I can't read it. It's the
Well, that's
font's
pretty
so
small, hey? 0.84 plus 0.54 times x minus 1.
Okay, it's so 0.54 is not far from.
I'm just going to make that a little bit bigger, just to make our life a little bit easier.
Okay.
That help, Matt?
that's good.
Okay,
So the slope is at 0.54. So we know from previous that the slope is cosine.
and that's what we have down here. Cosine of 1 is 0.54.
And the cosine is 0 at pi over 2. So it should be
Yeah.
close to pi over 2, right? Is that true? Not the slope. The slope, you know what?
Cosine goes between 0 and 1.
Yeah, so it's going to
Nice
go to
one.
0 at the
Yeah,
top.
it'll go to 0 at the top. So this is a kind of a small slope, about a half.
It's about
Let's
a-
rotate it. And there we get the equation for the other line. You can see the slope is different. It's pointing up more. It's 1 over 0.15, which is about a slope of 2,
Right, as it should be.
as it should be. Now, the thing we have to be careful about is this is the slope of the function, but at the value of y equal 0.84. So there's two things to notice. First of all is we did get the reciprocal slope, but it's cosine evaluated at 1, which is the value on the vertical axis. We'd like to know how it connects to the 0.84.
But we know the relation between cosine and sine.
That's right. So do we want to work this out now or on the next video?
Let's start with, we got the example here. Let's just see how that works.
Okay, so we'll keep this in mind for our next video. We noticed that the slope of 0.54 switched to 1 over 0.54, which is 1 over the cosine of 1. We'll see how that connects to this 0.84
Okay,
in the next video.
sounds good.